This is WK4.A. We're going to be looking at work and how it causes a change in kinetic energy in this case. So the scenario is we have a cart starting from rest. It's 1 kilogram. It's going to move on a horizontal surface that's frictionless when it's pushed with a force. So we have force versus displacement graph, which is something new. Haven't really seen necessarily one of these before, but it looks like the force applied is constant for the first 12 meters, and then the force tails off as the displacement goes from 12 to 20 meters. We're going to really just be looking at that first 12 meters. So before we get going, I'm going to actually start at what might seem a little bit odd place. I'm going to remind us of some kinematics equations because we're used to working with time equations, but this graph doesn't really have anything to do with time. So we remember that if we're looking at our original kinematics equations, we have a velocity equation and we have a displacement equation that these look like this. And then we combined those two together and eliminated the t. So we had a version of these that really was not based on time. So final velocity is equal to an initial velocity plus 2 times a times displacement. That's the delta x. So as we try to move towards a displacement sort of understanding, it'd be good to get rid of that time variable, which we have just done there. And then I want to rearrange this even a little bit further. I want to, first thing I want to do is I want to remove, well, not remove, I want to divide through by 2 on both sides. And then I also want to multiply through by the mass of the object. So I'm going to multiply through by the mass on both sides. So this is just algebraic manipulations here, not really stating anything new. Okay, so this 2 actually should go away. I divided through by the 2. So let me fix that real quick before we go any further. Okay, so that's the correction. And then what I want to do is remind you that Newton's second law says that the force is equal to the mass times the acceleration. So ma shows up right there, so I can rewrite that simply as there we go. And then one further reminder is that work, we've defined work as force times a displacement. Force times a displacement. There's also a cosine of angle term, but in this case, we've got a cart that's being pushed by a horizontal force along a horizontal surface. So the force and displacement are in the same direction, so that cosine term is just equal to 1. So work is just here force times displacement. So what I have here then is simply now let's define something new. Let's define what we would call kinetic energy. Kinetic energy, we'll define it as being 1/2 mass times the velocity squared. So if we define that, then what we notice here is that kinetic energy shows up twice in this equation. Here's what our kinetic energy would be finally, and here's what our kinetic energy would be initially. So if I wanted to just rewrite this, simply I have the final kinetic energy is equal to the initial kinetic energy plus the work that we do on the system. So what does this say? So by applying work, I change the kinetic energy from whatever it started at to whatever it ended up at. So this is kind of a general description of how work can change the kinetic energy. So if we are wanting to make a claim that the cart will have a change in mechanical energy of 48 joules as its displacement is changed by 12 meters, so I really just want to look at this first 12 meters, then all I need to do is understand, a change in kinetic energy comes from work. Well, one thing we need to do first is define what this mechanical energy means. Our book doesn't actually even use this term, but mechanical energy is defined in most books as simply the sum of the kinetic energy plus the potential energy. And the potential energy typically can be made up of a couple different forms. We've got gravitational, we've got elastic, and there's also electrical, which we will discover later in the year. We're going to be sticking to gravitational elastic in this unit, but mechanical energy is typically defined that way. In this case, since we don't have any springs in the system, there's no springs to have any elastic energy, there's no electrical components that are going to pick up any potential energy, and there's nothing that's getting any higher above the earth, there's no gravitational energy, so any amount of work that we do is going to end up changing simply the kinetic energy. So let's go ahead and figure out, well, what is the evidence that supports this claim? Well, we know that from this analysis that the work that we do is going to cause a change in kinetic energy. So, and we know that work is force times displacement. Well, here's our force, and here's our displacement. So maybe we can just use this graph simply to multiply the two together. So if I would notice that along this axis I have the force, and along this axis I have the displacement. If I want to multiply those two together, essentially what you're doing is you're calculating the area of this rectangle, or the area under the curve, and in this case that would amount to simply a force of 4 newtons, a displacement of 12 meters, so a total of 48 Newton meters, and a Newton meter we'll find is the same as a joule, which is our units of energy. This area, so the area underneath the curve is simply the work that we are doing on the object. So that amount of work, as we've seen here, is going to translate to a change in the mechanical energy, in this case kinetic, of 48 joules. This claim makes sense because the work done on the cart is equal to the change in kinetic energy, or you could say mechanical energy. Would be the more general case. Now, if we wanted to then determine the final speed of the cart, we can just refer back simply to this equation right here, and we note that the work done on the cart causes a change of 48 joules in kinetic energy. The initial kinetic energy is 0, so the final KE must be 48 joules, and that would be equal to 1/2 mass times the final velocity squared. That's how we've defined kinetic energy. So final velocity would be equal to 2 times 48 divided by the mass, and the square root of that, so square root of 96, since the mass is 1 kilogram. So that's the final velocity. So So on the grid to the right, sketch a graph of the acceleration of the cart as a function of displacement. Well, Newton's second law says that the acceleration is the force divided by the mass. The force here is simply 4 newtons. The mass is 1 kilogram, so it's 4 meters per second squared. So if I was going to graph that over the first 12 meters, it would just be a straight line. Angela says, hey, we know that the slope of the velocity graph represents the acceleration. So we're going back to our kinematics graphs here. Since the acceleration is constant at 4 meters per second, the velocity should be aligned with a slope of 4 meters per second. So what she's theorizing is that since our acceleration graph is constant, we would expect our velocity graph to be a straight line with a slope of 4 meters per second squared. Seems reasonable. What's the problem? Well, the problem is that she's mixing up a acceleration displacement graph with an acceleration time graph. The acceleration time graph being constant causes the velocity time graph to be a straight line with a slope equal to the acceleration. That's not what we have here. Really, we can't get any information necessarily directly from this graph. So we could say something like Angela is mixing up velocity time, well, no, actually the acceleration time graph with the acceleration displacement graph given. Now, if we really wanted to see what the velocity displacement graph looks like, which is what this next graph is asking us, we're going to need to actually do a little bit more work. And I think that the best way to do this is actually to go back to what we had way back here and use this work that we've already done. Because here we have information in this equation about velocity and displacement. So let's go ahead and transfer that. Let me just transfer that down here before we do any more work. 1/2 the final velocity squared is equal to 1/2 the initial velocity squared plus a delta x. And our initial velocity is 0. It started at rest. So we can drop that out. So the final velocity is going to simply be equal to the square root of 2a delta x. So now we have a velocity versus displacement relationship. Well, what would that look like? If this is, we know the acceleration is constant over those first 10 meters. What would this relationship look like? Well, it certainly wouldn't be a linear relationship. It would look like a root relationship, which kind of has something that looks like that qualitatively. So if we wanted to get a linearized version of this, if we wanted to get a velocity displacement graph that was linear, we have to linearize this by plotting velocity versus the square root of x, and then we would get a linearized version of that. So this part F, I've pretty much walked us into that answer. This was essentially where I started. So I felt it was actually better to actually start with that equation here than try to do this problem without that. So you might have struggled with this coming up at it from a different direction, but I wanted to get us there from that way. So this would certainly be how I would answer that, but I've already created that graph. Okay, that's it.